Hello everyone, welcome back to another random coder video. Today we'll be going over a reinforcement learning algorithm called the Monte Carlo tree search. So this algorithm is typically used to play games, specifically multiplayer games, so games with maybe 2, 3, or 4 or 5 players, in which basically you take turns playing, but with modifications of this, you could also have it where it's a multiplayer spontaneous game as well. But the idea behind this program is it chooses the best actions based on the heuristics. So kind of like game experience, and it'll choose the best actions that leads to the state that has the best chances of winning. The idea is to simulate a lot of games from a given state. So it could be the initial state, could be this state. Depends on kind of how many turns you've been into. And then you see from this state, you just simulate it with random chance. So it's random gameplay. And you simulate it a bunch of times. So then the law of big numbers will tell you which states are inherently better than others. Then the agent will make the action that leads to the state that gives the best chance of winning. So if player 1 made a move and player 2, this is player 2, let's just say you're playing as player 2, then you would choose the best possibility here that you can lead to, and then choose the action that corresponds. So just a little bit of how Monte Carlo tree search works. I have represented the circles as nodes in the tree. Each node represents the state and has some information. Now, the most important one here is the Q and N. Now, these are just variable names, so you can rename them if you want to. But for me, Q means the total amount of games that's won, and N means the total amount of games that's played. So if you can spot this, Q over N is just kind of the probability of winning in this state. All right, so each state has a Q and N, and then each state has a set of children. So for the initial state, for this setup, we're saying each state has 3 possible actions. So for this initial state, you have 3 possible children, and each one has 3 possible children. I didn't draw it out here because it was going to take up too much space. Okay, so let's go over a little intuition of how to do this Monte Carlo tree search. So there are 4 stages. The first one is select stage. The second one is expand. The third one is simulate, or some people call it rollout. And then the fourth one is back propagate. So these are kind of the 4 stages of MCTS, and the whole algorithm is just 1, 2, 3, 4 repeated many, many times. So let's go over how select works. Select is where you want to select a leaf node that has either not been explored or according to the function provided here. So let me move this a little bit. This function is called the upper confidence bound applied on trees function, and it is this equation right here. So this equation is Q over N plus, this is what we call the exploration value. And this is times the square root of log n parent and your own n. So this is n parent. I'll make it clear here. And just from basically what this function does is it allows us to balance exploration versus exploitation. And this is a common problem in reinforcement learning where you want to explore, but you also want to keep refining your own strategy. And this provides a nice balance. So the first part of this equation you can see is kind of its probability of winning. So the bigger it is, the higher the value. The second part is kind of the exploration part. So as you can see, the log of how many times the parents have been visited, as that increases, this side also increases. Or if the n has not been visited a lot, it also increases this side. And the exploration value, well, if the bigger it is, then the more likely it is that you value exploration over exploitation. So how we select is we traverse the tree, and then we keep using we traverse to the child with the largest value. So that just assume this child has the largest UCT, and then this child has the largest UCT among these three. So we're here. So we're at a leaf node. Then what we're going to do is we're going to expand this leaf node to have its children. So these are all empty right now. And then we randomly select one for the children. So let's just say we select this one. And then we go out to the simulate mode where we just simulate a random game. So we simulated that. That just say blue won. So blue is winner. And then what we do now is we back propagate. So given blue is winner, this is a red stage, right? So this is a player 2. So there's no reward here. This one gets a +1 for the Q, and then 0 and +1. And n always increments. So n is going to increment every single time. So kind of a way to visualize this. This is from Wikipedia. So you're at initial state. You're going to select a node. Now here they didn't select the leaf node. There's two ways to do the expansions, right? The first way is you either add all children, which is the way we're going to do it. The second way is to add one children at a time. Sorry, one child at a time. And this way, you need a lot of memory. But I think just adding all children is a easier implementation to do it. So for here, they actually select a node with incomplete children nodes, where their expansion state adds a children on there. And then since they only add one children, this is the children that they're going to use to simulate it. So they simulate with random chance. That's the result. And then the results gets back propagated back up the ancestors of this leaf node. So that's the general idea of MCTS. So now we are going to go to our code and then see this program in action. So let's go first to the game that we're playing today. So the game that we're going to be using to play MCTS is going to be Connect 4. And basically, we have the board. We have who's playing. We have the height of every column. So that's this height. And then we also have the last played position to check for our win. So these functions are rather self-explanatory. The code will be provided on my website, so you can feel free to check that out. But basically, the only code that is a little intimidating to look at here is just win condition checking. I didn't really condense it, that's why it looks a little intimidating. But the idea behind this is just, given the last played position, you just check around the 7x7 grid for a possible win. And once you do that, you can return the winner, or you can return if there is a winner or if there isn't a winner. And we have the game over, which returns if the game's over. We have who won, and then we can print out the state, which prints it like this. Okay, so to our MCTS class, basically, this is our node class. So let's go over this first. You have your Q and your N that we went over. You have your parent. You have which move this is that led to this state. And you have who won, right? But for our implementation, the only ones we actually need is these five. All right. So our add children, we just provided a dictionary of all children to add, and it'll add the children here. Our value is just based off of our upper confidence bound function. So it's q over n plus the exploration variable times the square root of log n of the parent divided by n. And we're saying if this just hasn't been explored yet, we're prioritizing that. So we're giving it infinite if you are exploring, which I don't see any reason for explore to be 0. Okay, so now for the Monte Carlo tree search class, we have our we have the few functions that we have called select, and then we have expand, and then we have rollout, and then we have backpropagate. So select is pretty simple. It's just as the knowledge, just as how we went over. So you select the best value or the maximum value of your children, and then you select that node, and then you keep choosing that node, right? So you move it to this node, and then basically, if you meet a child node, so while you're not at a child node, and if this just hasn't been explored, then we want to do that. So we'll do this, and then we're if it's none of these conditions above, we're going to expand the children of this node. And if it is expandable, so either it's not game over, and there are moves left, we are going to choose a random children that we expanded, and then we're going to return that. And this is going to be used in the rollout. So this node in this state is going to be used in the rollout. And then next thing we have is expand. So basically, as long as the game's not over and there's legal moves left, we just add the children. Nothing too bad here. Rollout is pretty simple too. Given a state, we're just randomly moving and then see who wins. Back propagate is not bad either. Basically, the only important thing here is the the value of our turn is the next player, not the current player. So if the outcome is equal to the next player, then that's 0 reward. Otherwise, if the outcome is equal to the current player, then it's +1 reward. So to do this, we need to make sure that there are parents left. So as long as the parent is not nothing, we keep going up the tree. And for each one, you add 1 to the total amount of games played, and you add the reward, and then you traverse it up with node equals node parent. And then if it's a draw, there's just always no reward, so it doesn't matter. And then if it is not a draw, then you just flip the reward, right? So it's either 1 or 0, because as you traverse up the tree, the players switch. So one level is player 1, the other level is player 2. So you need to switch that in the back propagation as well. And then to combine it all together, Monte Carlo tree search is an algorithm with a time limit. So you have a budget. Now we'll start the CPU clock right here, and then while there is time left, we'll keep repeating these 4 steps. So we select a node, right, and then we roll out this node, and then we back propagate the results, and then we add 1 to how many we've rolled out so far. And at the end, we just save these every single time just for some statistics. And then at the end, we have a few functions left. This function is called best move. So one thing I didn't go over here is how to choose the best move. We know that a good state will have a high UCT value, right? And we usually choose the high UCT value. So if the state has been visited, so if the n is big, then that means it's a good state. So in our code, basically we take the max n, and then we return the move that leads us to the state with the most explored values. And then this move is pretty similar to kind of actually moving in the game. So let me draw out a few things here. So imagine right now you're at your initial state, right? And you're making it, the MCTS agent's making an action. So it basically builds this tree, right? And then I'll simplify this for now. So it builds this tree. And then it's like, okay, I want to go to this state. So now it goes to this state, and then the human or player two makes an action, which leads it to this state. So now the MCTS actually starts searching at this node and then forms another tree, right? Or builds on the current tree, I should say. So basically, that's what it's doing. So as you make moves, as moves are being made, you need to move your root of the tree down to the current state. So that's what we're doing. Um, like we're just finding the move in the children, and then we're setting the root to be that children. Um, and then if it is not in the children, then that means we're player two. So we just set the root to be player two. And then there's a function for some statistics which returns how many we've simulated and the total runtime. So let's take a look at kind of the parameters we used. The exploration parameter that we use is just square root of 2. That's around 1.4. So yeah. And then to see the game work, this is 0 indexed. So I'll make a move, and then the computer will think in the actual game file, which is right here. I budgeted it 5 seconds to think. So, I just instantiate a state, instantiate the MCTS agent, and then it lets the user choose a move, and then it moves the tree down, and then it lets the MCTS choose a move, and then it moves the MCTS move, and then we just keep going until the game is lost or won. So right here, I budgeted it 5 seconds, but um, the general idea is that the higher, the better this MCTS agent will do. But with an efficient algorithm to check for the state for the win and a pretty good processing computer, 5 seconds should do most of the time. So as you can see here, in 5 seconds, it rolled out 10,000 games. So, and then it made this move. So I'm just gonna keep moving. Note that I am not a very good Connect Four player, so this might end up pretty bad, but we'll give it a shot. So as you can see here, when the states are still relatively like undeterminate, so kind of if you don't know who's winning or who's not, and it's relatively early in game, the MCTS agent actually, it actually doesn't roll out a lot of games. But you'll see that as we finish the game, or as we reach more towards the end, then the MCTS agent actually will start making way more moves. So you can already see that it's making more simulations as we go. And of course, if you do want it to play at a higher level, you just increase the number of seconds that you gave. So I chose 4. I'm going to block it. And right now, it actually seems like I might be doing okay. So hopefully, we continue this. And then it made a move. Oh, maybe we're not doing okay. Yeah. So the great thing about this is actually learns off with heuristics, and Connect Four is a game that lets you do that. There are some other games that you can also do. For example, Tic Tac Toe is a game that you could do for Monte Carlo Research, but you can always just brute force and find the solution that way. Um, a few years ago, the AlphaGo algorithm is kind of a combination of Monte Carlo research with deep learning. So Go is another game, and let's see, choose two. I'll choose two as well. 0, 0. I think it might come down to a couple of the last moves here. So I'll go with 5. And then, oh, so I did lose. But yeah, it had a Connect 4, and it won with actually a Connect 5. But that's kind of a proof that your algorithm is working. So kind of that's the idea behind the Monte Carlo tree search. Um, my code will be available online. So if you just click the link to my website in the description, you will see the code for this algorithm. So I hope you enjoyed learning about this reinforcement learning algorithm, and you can successfully implement it to play whatever games you wanted to play. And if you liked this video and learned a lot, make sure to subscribe to my channel and give it a like. And if you have any questions, you can comment it in the comment section and I'll respond to that. And I'll see you guys next time.